I've got your demand estimation calculations, and it's my intention to begin looking over them this weekend, and I hope to provide you feedback next weekend, sometime next week, so that if you want to make corrections during spring break, you can. But you don't have to wait on getting the corrected feedback on the project to begin laying out your pipe network and even to start setting up the analysis of it. It's very easy to change the flow rates out and have the model adjust. So you can begin the preliminary setup of the next phase of the project even before you hear back from me. Your next assignment is due on Tuesday the 11th. That's those problems indicated in Chapter 8. I know some of you have already started on that because I've got a couple of questions. We'll go over one issue of the best hydraulic section that ties into the last problem there, problem 25. But for the most part, I think that you could have already started that homework set based on the topics we discussed last time. Now, the highest, most important holiday in the hydraulics calendar is Hydraulic Jump Day. And Hydraulic Jump Day, we're going to celebrate this year on Thursday, April 10th. That's when all the stars will align, and we're going to go back into the lab and play around with the flume and look at the hydraulic jump and do some calculations. And so I'm going to bring in some refreshments. I'll provide the refreshments, but if you want to wear the correct attire for Hydraulic Jump Day, the correct attire is a blue afro wig. And so I've provided a link to where you can go and get one delivered to you for $4 off of eBay. So I'll be wearing a blue afro wig. All right? So I hope that you will invest the $3.99 shipped to come properly attired on Hydraulic Jump Day. All right? And I'm working on what's the correct song. If you have any suggestions for what's the correct, jingle, you have to have holiday music. It could either be crisscross, jump, jump. And then there was another one that we've had in the past. I don't remember what it was, but, oh yeah, Van Halen, jump. So those are all, that's the season, it's the reason for the season of Hydraulic Jump Day. Thursday, April 10th.
Something to do with jump.
All right. Maybe. Any questions about the announcements? Put it on your calendar. Order now. All right. So the next step of your design project is to start sizing the pipes. And here I've provided an image. It's kind of an unusual image. When you first look at it, you wonder if maybe it's upside down. But actually what this is, it's a 3D map of an underground pipe network. And so we're down below looking up, and the surface that we see is actually the ground. And you can see that there are pipes moving around with laterals, and those pipes have different slopes. You're going to go through this phase of designing the pipe network that's needed to accommodate the flows you estimated in the demand estimation. In demand estimation, you said how much water those people are going to be using, and so now you have to get it to their house. And for obvious reasons, it's really bad if you don't get enough water there. It's a critical thing, and the incident in Charleston illustrated it beautifully, how important water is to the economy. The economy was crippled when water wasn't available. Industry shuts down. I prepared this slide a long time ago, but I mean, these predictions are all true. Green areas die if it was the summertime in the west. If the water is a no-use order, everybody's lawns would have been just crispy because it doesn't rain enough out in the west for lawns to go unwatered. Now, in the case of Charleston, buildings didn't burn because water was still in the pipes. It's just it wasn't fit to be used for drinking purposes. But if you undersize a pipe network, then the fire department can't get enough flow out of a hydrant to fight fires. And so it actually becomes not only just a social inconvenience and an economic inconvenience, but it becomes a safety issue as well. And people really suffer when you undersize a pipe network. Well, remember that there's a limit to how much suction you can generate. You can only generate enough suction before your pump starts to cavitate. And so in theory, maybe if your toilet was at the same elevation of the pipe network, But that would seem probably, there'd have to be a real special set of circumstances that could happen. I mean, it wouldn't come out of your toilet because that's actually open flow. It's open to the atmosphere, but they might be able to draw some of it out of your pipes, maybe. But it's probably far-fetched. So how big should your pipes be? You're going to have to carry the larger of the two design conditions that you've just estimated. You've figured out how much you think the maximum daily demand plus fire demand is. And so you add the NFF that was provided along with that average daily flow during the maximum day. That's one possibility of how much water is going to be needed. Or you look at the peak hourly demand without the fire flow. So those are the design conditions. Now, other criteria that it says in the assignment description you have to follow is the pipe network pressure should be between 240 and 850 kilopascals. What is pressurizing that pipe network? Why is it under pressure in the first place? Because of what? Elevation head. How is it getting head? How is the network getting head? We've got a network that looks roughly like we got two loops and then one over here, something like that. We've got hill. We've got this little symbol here that represents where the well is. So why is it that at each of these junctions, why is there going to be pressure? Okay, from the spring, there's actually going to be, between the spring and the town, there's going to be a tank somewhere. Part of the design process is you're going to decide, I'm going to put a tank here. And not only you're going to say how big that tank is, but you're going to pick where on the map to locate the tank. Because where you put it on, which contour you put it on, controls the pressure at this point. This is a control point. When water comes into just one location, the pressure that you've got here affects the pressure everywhere else. So when you make the pressure bigger here, it will make the pressure bigger everywhere else in the network. And so the way that you're in the driver's seat as an engineer, and you've got some levers that you can pull on to make the vehicle do what you want it to do, and one of the things you control is where to put the reservoir. Because where you put the reservoir pressurizes. Pressure is delta H divided by gamma, right? So you can, yeah, it's the head divided by the unit weight. Or have I got that backwards? Head, newtons. I'm just throwing this together real quick. Let's do the full energy equation, because that's what you're essentially doing is you've got from 1 to 2 doing the energy equation. So we've got pressure 1 divided by gamma plus Z1 plus V1 squared divided by 2G equals P2 divided by gamma plus Z2 plus V2 squared divided by 2G plus head losses. Okay, so between 1 and 2, there's going to be some pipe length, and WaterGems will keep track of how much head loss there is in the pipe. You should make this pipe pretty big. This is one pipeline that you don't want to shortchange the size on. I mean, don't make it a meter in diameter if it doesn't need to be, but this is more flow is going to be going through this pipe than any other in the entire network. Gil?
So we can't have a pump anywhere else?
No. We want this just to be gravity fed. It's a wonderful opportunity for us to save on electricity if we can have the water flow by gravity from the spring into the reservoir and then pressurize the town. But if we didn't have that nice hill next to our town, then a pump is what we'd be forced to use. Yeah. Yeah, you've got a lot of elevation difference there. And so, here at 1 where it's a reservoir, we have no pressure because the reservoir is open to the elevation. We've got no velocity head because the water in the reservoir is not moving. Z2, you can look up the elevation because you've got contours through the town as well. So you'll know the difference in elevation between wherever you pick where you're going to put the reservoir is the elevation that you would put into the energy equation. Actually, looking up the elevation off the map, you'll put the elevation at each of these points. You'll have to type in the elevation of the point. The velocity head will automatically be neglected within water gems, and it'll calculate the head loss. And so there's essentially the pressure at 2 is governed by the elevation difference between 1 and 2. Did you have a question?
Yeah, so we got to keep track of what our depth of our reservoir is.
Well, we won't have to take it that far. What we'll assume is that you're going to put the reservoir, and what you have to put into water gems is the water elevation of the reservoir. And so you can just say, you're going to put the tank at a certain place, and if you want to say, I want my water elevation, when you size the reservoir, it's maybe going to be a certain diameter, and you're assuming when it's full, it's 3 or 4 meters deep. But that's a good point, that the water surface and the ground surface aren't the same thing. And so, yeah, you may have to move it a little bit higher up on the hill than you anticipated because it's the water surface that counts. Another issue that comes up sometimes is, well, how deeply are you burying the pipes? Because the pipe and the ground elevation aren't the same. When you walk around in Huntington, you don't notice the pipes at ground level. They're buried. So I've given you the contour of the ground elevation. So as you enter the elevation in all of these junctions, what you might do is just have a standard offset. Assume maybe that the pipe is buried 1 meter below the ground elevation at each of those locations. Just keep it a standard thing. Okay, there's a range of pressures. 240 kilopascals is kind of an accepted minimum, and the reason why you don't want to go lower than that is because if it's much lower than that, there's the possibility of backflow. And backflow is when maybe water would go from a high part of town and start actually, instead of going towards people's homes, if someone was living up on a hill and the pressure below them in the network was low, during a low period of time, the water could go from their homes back towards the rest of the distribution network. And so water has the potential to flow the wrong way if the pressure is too low. And besides that, buried pipes may have water seeping into them if the pressure gets really low. And when you've got water pipes crisscrossing with sewer pipes that may be leaky, you want to make sure that no inflow is getting into a drinking water pipe. And so there are a couple of reasons why you, even just beside the comfort and convenience factor, that you want the pressure to be at least 240 kilopascals. And then 850, that's an upper limit that's driven by the usually the water heater that people have in their homes is sensitive to excessive pressure, and if the pressure is too high, then it can cause the seals in a water heater to begin to leak. So now here's the thing, is that at night, when people aren't using very much water, during the low flow condition, the pressure is going to be high. But then during the day, when there's a lot of water demand, the pressure will go down. So why is it that the pressure is fluctuating if the reservoir location is fixed? Why is it that the pressure is going to change over the course of the day inside the town? Because the flow rate's changing. Well, so what? What's the relationship between flow rate and pressure? Okay, velocity. If the flow is high through a pipe, then the velocity is high in the pipe. And then, if the velocity is high, there's more resistance. So there's more friction losses if the velocity is high. And so if there's a lot of friction losses, then you're losing pressure. Because remember, head loss due to pipe friction is FLV squared divided by D2G. So what I'm saying is during the day, when people are using lots of water, as the demand goes up, so does the velocity. So if you've got a fast velocity, that means you're losing a lot of head. And so what's the consequence of having head loss in this pipe is that the pressure downstream is lower than it would be than at night. And so the guy at the end of the network, he can't figure out what's going on because he'll get up in the middle of the night to take a shower and the pressure is great. He's got 850 kilopascals. And then at 8 p.m. on the peak day of the year, on the peak year of the entire system's lifespan, he's only got 240 kilopascals. But that's okay because that's all you have to do is provide the minimum. And to provide any more than the minimum design criteria is inefficient by definition. Engineers are trying to just cut every unnecessary luxury and give them 240 at high design flow and 850 at night and nothing extra. All right? Sounds heartless, but they're the ones who are also paying for the network, and so the only way this guy can have constant pressure all the time is to make the pipe bigger than it really needs to be. But the criteria say that 240 to 850 is acceptable. So the reason why there will be fluctuation and loss of pressure is because of pipe friction.
What's the flow rate out of the reservoir?
Good question. So when you size these pipes, you're going to assume that it's the peak condition. Now, you went through and you decided what's going to be the peak flow in each loop. Here maybe this loop the peak was peak hour. Maybe in this loop it was peak day plus fire, and here it was peak hour. So you find what's the design flow rate, and then you've got a certain Q coming in, a certain flow rate coming in here. You found out what all of the flow rates in are. You've got all your Q's defined, and so the flow here is going to simply be the sum of the flow rates out. And WaterGems will automatically figure out how much water needs to come out of the reservoir. The only thing that you specify in WaterGems is the demand collections at each of the outlet junctions. Yeah.
Can you give us a ballpark number of what ours, like the range?
Of flow rates?
Ask that question.
I mean, it's so variable. 100 liters per second. I mean, if you want order of magnitude, I think 100 liters per second would be for some of them in the range, but you'll know more soon. Yeah.
Since the reservoir is open to the atmosphere, wouldn't the elevation of the water surface be the same as the spring is at?
No, because we're going to put the springs higher on the hill. So we're not going to put the reservoir all the way at the spring because that actually might be too much pressure. If you look at what's happening at night, when the flow rate is really low, then you don't want to put this all the way up on the hill because it could give you excessive pressure at the low end of the network.
You flow right out of your reservoir though to the tank.
You mean from the spring to the...
Spring to the-
Okay, so the flow rate from the spring to the reservoir, we're going to talk about that in detail in a future lecture when I teach you how to size the reservoir. But the quick answer is it is the average daily flow that you're going to have coming out. So basically, what I'm saying is that in a 24-hour period, the water that goes out is going to be balanced out by the flow that comes in. So for now, don't let that trouble you because it'll be clarified in a future class period. But what you should be doing on the lecture now, or on the project, is import that image that I gave you. And there's instructions in MU Online that explain how to import it. I've scaled that image so that 1 pixel equals 1 meter. So it's really easy to import. And then start drawing your pipe network on top of the little lines that represent pipes. Start identifying where the junctions are that demand is going to be coming out of, where you're going to have the Q's coming out. Start putting in the elevations. And remember that be sure that you start in the right unit system because when you start up it could be in traditional units and you want to be working in SI. And so start laying out the pipe network, and then when I get back to you on your flow rates, then you can start seeing how big the pipe needs to be. And so what you should start off with is make all the pipes real small. And then gradually increase the size of pipes one by one. It's sort of like a little puzzle. You say, well, this is an upstream pipe. It's going to have a lot of flow going through it, so I'm going to make these two bigger than they were before. And you look, well, how did that change the pressure? And you should annotate the pressure at each of the junctions so that you can execute the model and see how the pressure changed. And then you make the pipe a little bit bigger. Execute the model, see how the pressure changed. Just to remind you of that process, I think I've made recordings, like screen capture recordings of how to set up a model, how to do annotations, and I'll send you a link to those recordings just to refresh your memory if it's been a while since you used WaterGems. Yeah, we've done a demo, and then I've also got a recording that I made in hydraulic engineering last year. So, I'll tell you that there is a feature in WaterGems where you tell it how much things cost, and then you say, design it. And it automatically designs the system. It goes through and it optimizes what's the most cost-effective solution. It actually creates 100 different models, and it picks the one that costs the least. But it's a little bit complicated. It's tricky to set up, and I won't have you do that until at the end of the design project. After you turn in all your work, then we'll have a separate assignment where I show you how to use what's called the Darwin Designer. But I won't try and hide the fact that there is an automated tool, but I think what's more important is for you to do this manually, and it won't take forever. I think you can optimize, once you get the pipe network set up, you can optimize it in an hour, 90 minutes maybe, if you're going to be really picky about it. But that's the process that we're going to be going through.
So your peak pressures, your minimum pressures would be when you're at your peak hour?
That's right, yeah. Under the design condition, when the flow rates are big, is when you'll see the lowest pressure. And then you'll go back through and you'll create another model where you've got all of those Q's set to 0, and you'll find out what's the pressure under static conditions. And so that helps you to figure out where to put the reservoir. You want the reservoir as high up on the hill as you possibly can without exceeding 850 when the flow rates are 0. Because the higher up on that hill you put the reservoir, then the smaller you're allowed to make the pipes. Because head is what you're spending to make the pipe smaller. You make the pipe smaller, you're going to lose some head. Well, all you have to do to get more is put the reservoir higher up on the hill. And so that's sort of what you're balancing, is the reservoir location versus the pipe size, and looking at the impact of all of that on the pressures. So I'm going to write a little note to myself to remind me to send you the link to the model setup video. All right. Any final questions before we move back to open channel flow?
So when actually designing a project in real world,
Yeah.
do you use traditional units or do you use SI?
It depends on the project.
Like what does it depend on?
It's usually a code, or the regulatory agency specifies it. If you're doing a project for, here in West Virginia, all the state agencies are required to use traditional units. But some federal projects work in SI. Yeah.
When I was searching for the I found like a 20 years down the road cost analysis for doing the entire pipe network from right down to the bottom. And I was looking at how they priced it and all, and they use all sorts of different units. Some stuff, there was some mix in between.
Yeah. It can get to be a mess. One of the things I wanted to show you, even though it doesn't fit exactly in with the content we're covering today, is a result of flow resistance. And that's what we've been talking about with Manning's equation, is what happens when a surface resists flow. And there are several different approaches that are taken to try and characterize the velocity distribution in a channel. Remember that when we've got water flowing downhill, the velocity of the water increases the higher away you get from that surface. So there's some sort of a velocity profile where the velocity of the flow close to the surface is small, and the further away you get from the surface, the velocity increases. Well, here's one equation that's been developed to try and approximate what the velocity is as a function of the distance from the bottom of the channel, y, and that's relative to a total depth of flow, d, where d is the whole depth of flow. And so if you wanted to find out what the shape of that curve looks like, then you can use the von Karman constant and this velocity distribution equation to come up with what the shape of that looks like. And so it can act a little bit weird when you get to really small depths. You'll notice that the velocity is actually negative. And so, depending on what variables you use, this equation performs reasonably or a little bit weird. But one thing I wanted to show you is the effective slope on velocity profile. And so the dark red velocity profile corresponds to a relatively shallow slope of 0.5%. And so you'd notice that the velocity up at the top of the channel is pretty close to the same as what the velocity is towards the bottom. But then the steeper the channel, so 2% slope now for the channel, you'll notice that there's a much greater difference in the velocity at the surface relative to the velocity at the bottom. And so that's one approach that's used to approximate velocity profiles. Sometimes average velocities are measured by finding the velocity at a certain depth. And so one rule of thumb kind of calculation is that if you calculate the velocity 4/10 of the, the velocity 0.4 times d. Yeah, so if you know the depth of flow and you multiply that by the velocity at, this is actually not a numerical equation. This is saying that the velocity at a depth of 4/10 is sometimes taken as the average velocity. So if this was a depth of 1.0 in total, then you can go down so that you're at 0.4, so 4/10 of the way up from the bottom. That velocity would be taken as the average velocity, or you could take the velocity at 2/10 of the depth and average it with the velocity at 8/10 of the depth. And usually the way that they'll measure the velocity at a single point is they have what looks like a boat propeller. It's a little impeller, and they put it down into the water and it spins, and there's a reading that'll come up on how quickly it's spinning and what that corresponds to into the flow velocity. And so they'll just sort of take velocity at a couple of depths, and that's how they come up with the average velocity for flow in the channel, is just to measure it at a couple of locations with a physical measurement and then take an average. Another thing that doesn't quite fit in exactly with what's in the textbook, but is important for you to just sort of have a handle on, is what to do when you've got a floodplain and have to come up with a composite or an average end value. So let's say that flow ordinarily is in this trapezoidal channel, and the material that would be in a main channel, it might be like a compacted clay or concrete or just plain soil. So you'd have one set of end values associated with this trapezoidal channel, but then you're going to have different materials in the floodplain. The floodplain can include grass, weeds, stumps, all sorts of trash, as we've talked about before. And so one of the common approaches for coming up with an average end value is the Horton-Einstein method. And in the Horton-Einstein method, what you do is you weight the end value based on the wetted perimeter. And so you would you'd multiply for each of these elements, the wetted perimeter of element 1, you'd multiply it by the end value of element 1, and then you'd add up all the different pieces. So you'd now take this second part here, and maybe you'd have an average end value for this, where you've got all the trash and weeds and debris, and you would end up coming up with a weighted average that is based on the wetted perimeter. There are other approaches that base the end value on area, but the advantage of this, if you think about it, the resistance is applied at the surface, and so rather than weighting it on an area basis, it really should be weighted on the basis of the wetted perimeter, because it's that contact length that determines how much resistance is applied. All right, so this is Manning's equation, and if we have a certain end value that we can't change, we're forced to use a certain material, and we've got a given slope, S naught, how is it that you maximize the flow rate based on this equation? You want to have a big Q, so if you've got a certain N that's fixed, and the slope that's fixed, you want a big Q with a big area and a small wetted perimeter. So the most efficient channel is one that minimizes wetted perimeter. And just to illustrate that, let's take these different shapes into consideration. What do all of these shapes have in common? All right, that's one thing. They're all rectangles. All right, the cross-sectional area for all of them is 20 square meters. Would you expect that all of them have the same flow capacity? Now, if you put that into Manning's equation, are you going to be able to get as much flow through this as through this one? I mean, even without knowing Manning's equation, if I just asked you instinctively, why is it that you'd expect the channel on the far left to not have as great a capacity as the one on the far right? What is it about that channel that makes you think you're not maybe going to be able to get as much flow through it? Why is there going to be more resistance? You're right, but why? Okay, there's a lot of, you've got a long wetted perimeter and it's narrow, so the flow just can't get away from the resistance. If you're thinking about it that way, you know, where is it the flow has the freedom to move without being under the influence of that no-slip surface? Remember, the no-slip condition is that water doesn't just move without any resistance over a stationary object. Actually, the water at the interface of the object has the same velocity as the object itself. So we've got a certain thickness into the water that has the laminar sublayer, and even on top of the laminar layer, there's still resistance. Whereas here, you know, in the center, it's far away from resistance, and so it's going to have more capacity because more of the cross-sectional area is far from resistance. And so let's do a spreadsheet example. I'm going to show you an illustration that just makes this point. How we know that we can find some cross-section that's best. Okay, so what I'm going to do is have the channel width B, Y is our depth, area, a wetted perimeter, a hydraulic radius, and then a flow rate in cubic meters per second. And for all of these, we're going to have the same slope of 0.01 and the same n value of 0.013. Let's go back here. Maybe I'll just copy this over so that I've got these to look at. Okay, so we're going to have one of them that is 10 by 2. So we've got one where the bottom width is 2 meters and the depth of flow was 10 meters. We have one that was 10 by 2 the other way around. We've got a 5 by 4 and we've got a 4 by 5. All right. I guess if I'm working from left to right, I should say that the bottom width was, this one was 5 and the 4. Oh, okay. There we go. Okay, so area is just going to be the B times Y for each of these, B times Y. So we're going to see that they all have the same cross-sectional area. And by the way, this process of what I'm going through right now is very similar to the last homework problem on your assignment. The last homework problem gives you a weird-looking shape. It says there's some channel that is straight on one side and inclined on the other. And you're going to try and minimize how much it costs to build this. And the solution I did for that problem actually is a spreadsheet solution where I try lots of different combinations to see what cost is the lowest. So as I'm doing this, keep in mind that this has a direct application to the last homework problem. So the wetted perimeter for these is, it's going to be simple for us to calculate the wetted perimeter here. It's going to be 2 times the depth plus the bottom width. So I'm going to do 2 times the depth and then plus the bottom width. So that's my wetted perimeter. In this case, you'd have to calculate the wetted perimeter of this inclined surface a little bit differently. You know, you'd find out the height of it, the horizontal component, and find the length of it according to the quadratic equation. Okay, hydraulic radius is area divided by the wetted perimeter. So we can carry that through. And then finally, the flow rate is going to be Manning's equation. And so I need to type Manning's equation in here. This is what I'm going to be entering in for Manning's equation. I'm going to do the equation on the far right is how I'm going to write it. So equals the area to the power of 5/3 times the slope. I'm anchoring that to the 1/2 power divided by n. Also want to anchor that reference, and then divided by the wetted perimeter to the power of 2/3. Okay, so any questions on Manning's equation, how I've typed that in? Okay, so now I find out what the capacity of that channel is if it was this 2 feet wide, 10 feet tall. So I can just drag it down and find out that of the options that are listed, the most efficient is this one. It's the one that's 4 meters depth, 5 meters width. But that's just the most efficient of the options that are provided. I could probably do a little bit better. So the way that you maximize flow is by what? We have to, in this example, the constraint has been the cross-sectional area has to be 20. So I'm going to do another one where I'm forcing myself to have a cross-sectional area of 20. So how do I get the best flow rate? The smallest what? The smallest wetted perimeter. I'm going to find that with GoalSeek because I don't like to mess around wearing out my fingers. So I'm going to use, actually I'm not going to use GoalSeek, I'm going to use Solver. Because GoalSeek, you have to know what the objective is. And I don't actually know what flow rate I'm going for. Because in GoalSeek, you have to say, all right, change this parameter in order to make some other cell equal to, and you have to type in the value you're going for. Whereas Solver allows you to say, play around with this other cell in order just to maximize the result. And so I'm going to use Solver, but it's the same thing. All right, so what I will do then is I have to get b times y must equal a. And so how am I going to do that? I'm going to say that y and b, okay, I'll have this be the one that I change. So I'm just going to start off with a guess value of 3. So I'm going to be changing this one. And therefore, y is simply a divided by b. Because remember, area is the width times the depth. And so what I'm saying is area must be 20, and I'm going to allow Solver to play around with what is the correct width, and so vary this, and then as it varies that, whatever it chooses, I have to have the y be such that the area ends up being 20. So is everybody with me? I didn't pick that y value. It's the result of a calculation. And so then the wetted perimeter is going to be the base plus 2 times the depth. The hydraulic radius will be the area divided by the wetted perimeter. And I guess I can just drag this down. It's going to be the same Manning's equation. It'll be area to the 5/3 power, slope to the 1/2 power divided by n, and divided by wetted perimeter to the 2/3. So Manning's equation is entered correctly. So now I go to the Data tab, and instead of what if analysis, I go to Solver, which is an add-in that you have to install separately into Excel. Click that, and now it gives me a few more options. Instead of having to know what value I'm going for, what I want, my objective is for this flow rate to be max. And I'm going to tell it should change B in order to make that come about. Now, these other options allow you to say, how close it has to be before the solution converges, but the default in this case is fine. We don't have to override the convergence criteria. So again, what we said is we want the objective to be maximized. And it will do that by changing the width. And so when it changes the width, it's also going to be finding the depth indirectly. So solve. And let's see what it came up with. We could get 208.8 cubic meters per second. That's the maximum. And what do you notice? The B and the Y. It looks like it's half. Yeah. I'm going to have it keep that solution. Okay, so it's keeping it. So what is B divided by 2? Well, there it is. It's our depth. And so the most efficient rectangle is a half square. And that's what we get to on this next slide that says there's different shapes. Let me just jump to this slide here, which says there's different shapes that have a certain best hydraulic efficiency. And for a rectangle, the best rectangle is a half square. We'll come back to this in just a minute. So since we mostly do trapezoids, trapezoids are the most common engineered channel. The best trapezoid has a kind of an unusual shape because the side slopes are much steeper than ordinarily we'd go for. A pretty common side slope would be 1 vertical for every 2 horizontal. But the root 3 divided by 3 is actually, I think, 0.577. And so that actually ends up being pretty steep, the side slope there. And so it would only be common for us to go for this best trapezoidal channel if we were working with a concrete lined channel. And usually it's not so critical for us to maximize efficiency that we'd go to all the trouble of making it that shape. But technically speaking, the way that you actually get that shape is it's the channel that if you draw a circle, it's the trapezoid that best approximates a half circle. And so it will intersect the trapezoid at the bottom, in the center, and on the sides as well. The circle, if you think about it, remember what we're trying to do is we're trying to minimize wetted perimeter. And the circle has the greatest interior area per perimeter of any shape. And so the trapezoid that gets closest to approximating the circle is the one that will have the most flow per unit of wetted perimeter. And so it has the characteristics of, you can calculate the wetted perimeter as a function of the depth y, the bottom width as a function of y, the cross-sectional area, the t value is constant, and the hydraulic radius is just area divided by wetted perimeter. And so the interesting thing about hydraulic radius is it's just the depth divided by 2. So that's kind of a unique thing.
What's M up there?
N?
Yeah.
Where do you...
Be equal
I'm not seeing it.
on the first.
Oh, here? Oh, sorry. It means T. T, yeah, because if you actually look, I took this figure from another text, and the way that they defined the side slope there was M instead of T. Yeah, I'm glad you noticed that. I forgot to change it. So let me just do this. Copy, paste, and put that right back up there. 2 times, what was it? TY. TY. All right, thank you for noticing that. So where it said M for the top width, change that to say T instead. So here are some other shapes that are like most efficient. And by most efficient, again, what we're going for is the shape that gets closest to the half circle in order to maximize the area that is away from the resistive surface. So here is the best triangle. It is a triangle that has a 90-degree angle down here because it's the one that allows us to put the most of the circle in there. And let's try this out. This is a combination of best, section, and Manning's equation. So hopefully you've taken the time to figure out how to solve equations on your calculator, because like I've said before, there's no escaping that need. What will be the flow depth? What is the y if we're going to do the best triangular cross-section, and we know the flow rate that has to be accommodated is 2.5 cubic meters per second. That's what we're trying to convey from point A to point B. We're going to use concrete that has an N value of 0.013, and it's a 1% slope. And so what will be the flow depth? So to solve this, use Manning's equation, and here are the formulas you should use for area and wetted perimeter. Use the triangle. Area is y squared, wetted perimeter is 2.83 times y. Feel free to collaborate with your classmates on this as you're working through it. In this, yeah, T is top width, right. All right. So let's take a look at where we're at with this one. We're solving Manning's equation, and we need to substitute in the formula for area and wetted perimeter in terms of the unknown depth. So Manning's equation ordinarily would be a to the 5/3 divided by n perimeter to the wetted perimeter to the 2/3 power, and then all of that is sloped to the 1/2. For the triangle that I've got here, which is going to be a triangle with a 90-degree angle at the bottom, the area is the depth squared, and the wetted perimeter is 2.83 times y. So I just put those formulas directly into Manning's equation, and now I need to find the y value that gives me the right-hand side equal to 2.5 cubic meters per second. Since one of you asked in a recent lecture, I'm going to force you to look and see what an HP calculator looks like. That's what I use. I don't know if that glare is going to be too bad. Let's see here. All right. This one actually isn't going to use the reverse Polish notation. You can get this emulator. I think they probably have it on, I know they do. They've got it on iPhones as well. This one's called Droid 48 is the name of it. No, you won't. But there's a similar one. They have, the calculator's an HP 48 calculator, and there's probably half a dozen programs that try and simulate what that looks like. So what I'm going to do is I'm going to tell it I want to solve. So this green one, and then up here to where it says solve. And it takes me into a variety of options. You can do differential equations, polynomials, solve finance problems like time value of money. I'm just going to do an equation one. And now I just typed in the equation before, but I'm going to enter it again just to show you what it looks like. I'm going to go to this colored key and then up here to enter because it's equation, and it has an equation writer. So the equation writer I want to do is Q. So it's got all the letters of the alphabet, which is kind of nice if you have been trying to like rewrite your variables for the Casio. You don't have to do that anymore. I don't know. I'd have to think about that. What are the risks of if I did? Yeah. So I'm just typing in the equation, y to the power of 2, and it even looks like an equation, which is nice. And to the power of 5/3. And this is not new technology. The calculator this is based on, I bought when I was a freshman in 1993. And this is emulating a calculator that's 21 years old. So I don't know why. All right, here we go.
Freshman in what, college?
Yeah, in college.
How come you didn't advocate the HP official calculator?
Well, Dr. Pearson has a point that it's good for you to be acquainted with the calculator that you'll use on the FE.
Oh, is that not legal?
This particular one is not because it has memory. Yeah, you could store equations and stuff. So I'm just writing the equation here, slope to the 1/2 power. Now I'm going to do divided by n And if I was paying attention, I could be typing this in faster than I am. And now I need to put in my formula for wetted perimeter, which is 2.83 times y. And then all of that is to the power of 2/3. All right. And then enter. So now it's translated in that visual mode. It translated the equation to what needs to be there in the solver. And so now I can put in the Q, 2.5, enter that in, click over to, ordinarily I wouldn't know this yet. This would have, it would be blank or it would have some wrong value. Okay, so I could type in the slope 0.01, okay, end value 0.013, okay, and then you just go over here to the y and you'd say solve. So you push that button and it thinks for a second, and then the depth is, for this one, y should be 0.851. And so when I was a student, what we would do in our homework assignments is we'd do this and then we'd say solver, and that would just be us explaining that we went from the equation, we put in all the given values and came out with the normal depth would be 0.851. And what's nice about having it this way is that then if I said, well, okay, that's too deep. What if I change n values? What if I had 0.012? If I finish my concrete more smooth, what is that going to do for me? And so I solve again. Okay, it would get the depth down to 0.83. Or if I wanted to say, all right, well, what if we made the slope 0.015? Then you can have it resolve for the depth over again. That would get you down to 0.76 for the depth. So this isn't the only calculator that's able to solve equations easily, but it's a good one. So if you want to download that, I'd encourage you to use on the homework, and if you do get into the habit of using it, I'd have to think about whether you could use it for an exam. Of course, you could actually buy the real calculator, and they're available for purchase as well. $100.
$100.
Yeah. Well, when you go in for surgery, do you want the doctor to use an X-Acto knife or a surgical scalpel? Professionals use professional tools is my attitude.
I saw something go across, I saw an email go out between a bunch of DOH engineers.
Yeah.
That was forwarded to me.
Yeah.
That said, how many engineers actually use HPs? And they were like, the email chain was like, no engineers.
No engineers? I don't know.
Oh, TI or guessing.
Was that West Virginia DOH? No, that's a joke. All right. So anyways, now, as you already know, calculator battles get passions rising in engineers. There's nothing that can get fists flying faster than which calculator is better. In my school, it was TI versus HP, and HP had more adherents than TI. But you use what you like. As long as you can solve the equations, I'm happy as a clam. Find the normal depth, and I'll be smiling. So that's all we've got for today. Let me just look over these announcements. I'll get back to you on those demand estimations as quickly as I can. You've got a homework due on Tuesday. And don't forget to order your wig. I'm going to get on eBay right now and get my wig ordered. Thank you. Not with me, no. That's it for today.
I'm going to get that calculator downloaded